Welcome to the final part of our journey through the history of atomic theory. In this chapter, we step into the revolutionary world of quantum mechanics. From Planck's daring quantum hypothesis to Schrödinger's groundbreaking wave mechanics, we'll explore how cracks in classical physics gave rise to a new understanding of the universe, transforming science forever. Scientists defined an idealized black body, an object absorbing all incident radiation and emitting a continuous spectrum of light when heated. Real objects like heated metal approximated this behavior. The spectrum's shape depended solely on temperature, suggesting a fundamental law of nature rather than material-specific properties. Early observations revealed that as objects heated, they first glowed red, then yellow, and finally bluish-white. Wilhelm Wien formulated this relationship mathematically in 1893, showing how the peak wavelength of emitted radiation decreased with increasing temperature. This became known as Wien's displacement law. Wien's law accurately predicted the wavelength of maximum emission, but calculating the complete radiation spectrum proved challenging. Classical physics suggested that higher frequency waves should carry more energy, leading to increasingly intense radiation at shorter wavelengths. Following classical principles, physicists calculated the expected energy distribution across different frequencies. Lord Rayleigh and James Jeans derived a formula predicting that energy should increase without limit at higher frequencies, contradicting experimental observations. This ultraviolet catastrophe threatened the foundations of physics. Classical theory predicted that every hot object should emit infinite energy at high frequencies, an obviously impossible result. The discrepancy between theory and experiment demanded a radical solution. Experimental measurements showed that high-frequency radiation was actually less intense than classical physics predicted. The energy distribution peaked at a specific frequency and then decreased, forming a bell-shaped curve. This pattern could not be explained using existing classical physics, highlighting a critical gap in scientific understanding. The blackbody radiation problem exemplified a growing crisis in physics. Classical theories that worked perfectly for everyday phenomena failed at atomic scales. This growing crisis in classical physics called for bold new ideas, paving the way for Planck's quantum breakthrough. In December 1900, Max Planck made a bold proposal. To explain blackbody radiation, he suggested that electromagnetic energy could only be emitted in discrete packages called quanta. The energy of each quantum was proportional to the radiation's frequency, with a new fundamental constant, later named Planck's constant, as the proportionality factor. Planck's quantum hypothesis accurately predicted the entire blackbody spectrum. His mathematical formula showed how radiation intensity initially increased with frequency, reached a peak, then decreased at higher frequencies. This idea shattered the classical assumption that energy is continuous, marking a radical departure in scientific thought. Planck's constant, denoted by h, emerged as a fundamental feature of nature. With units of energy multiplied by time, it set a basic scale for quantum phenomena. Its incredibly small value, approximately 6.626 times 10 raised to the power minus 34 joule seconds, explained why quantum effects weren't noticeable in everyday life. Initially, Planck viewed energy quantization as a mathematical necessity rather than physical reality. He hoped continuous classical physics would eventually explain his formula. However, Einstein's interpretation of light quanta in 1905 suggested that discreteness was a fundamental aspect of nature. Einstein proposed that light itself existed as discrete particles, later called photons. Each photon carried energy proportional to its frequency, following Planck's formula E equals hf. This bold hypothesis explained puzzling features of the photoelectric effect, where light knocked electrons from metal surfaces. While Planck considered energy quantization a mathematical convenience, Einstein proposed that light itself fundamentally consists of discrete particles. This fundamental difference highlighted quantum theory's revolutionary nature. Einstein's photon concept met strong resistance. Many physicists, including Planck, found it difficult to abandon Maxwell's successful wave theory of light. However, experimental evidence increasingly supported light's particle nature in phenomena such as the photoelectric effect. The concept of light quanta challenged wave-particle dualism. Light behaved as waves in some experiments and particles in others. This apparent contradiction defied classical logic, but accurately described nature's behavior at the quantum level. Einstein's work showed that quantization wasn't merely a mathematical trick, but reflected nature's fundamental discreteness. His interpretation of Planck's theory transformed quantum concepts from convenient calculations into physical reality, setting the stage for quantum mechanics' further development. Building on Einstein's quantum insights, Louis de Broglie extended the quantum revolution to matter itself. In 1924, de Broglie proposed a revolutionary hypothesis extending quantum concepts in an unexpected direction. If light waves could behave as particles, he reasoned, perhaps particles like electrons could exhibit wave-like properties. His mathematical formula linked a particle's momentum to its wavelength through Planck's constant, unifying particle and wave descriptions. De Broglie's theory predicted that a particle's wavelength was inversely proportional to its momentum. This meant heavier or faster-moving objects would have shorter wavelengths, explaining why quantum effects were readily observable for electrons, but not for larger objects. His formula, wavelength equals h by p, became a cornerstone of quantum theory. De Broglie's matter waves weren't just mathematical abstractions. In 1927, Clinton Davison and Lester Germer demonstrated electron diffraction through nickel crystals, producing interference patterns characteristic of waves. This groundbreaking experiment not only confirmed de Broglie's theory, but also cemented the wave-particle duality as a universal principle in quantum mechanics. The discovery of matter waves completed the symmetry between particles and waves in physics. Just as light demonstrated both wave and particle properties, matter exhibited this same duality. This universal wave-particle nature demanded a new mathematical framework to describe quantum behavior fully. In 1926, Erwin Schrödinger developed a mathematical equation describing matter waves' behavior. Unlike de Broglie's individual waves for each particle, Schrödinger proposed a mathematical framework that described how particles in a system interact and evolve over time, using a single equation. Schrödinger's wave function evolved according to precise mathematical rules, providing a powerful tool for calculating quantum behavior. Schrödinger's equation revealed that quantum systems' behavior differed fundamentally from classical physics predictions. The wave function provided probability distributions for finding particles in specific locations rather than definite trajectories. This probabilistic nature became a defining characteristic of quantum mechanics. The new quantum mechanics unified various phenomena under a single mathematical framework. Schrödinger showed that his equation governed how wave functions change over time, with the rate of change proportional to the system's total energy. This relationship enabled precise predictions of quantum behavior. Schrödinger's formulation represented quantum mechanics' mathematical maturity. By describing all particles through a single universal wave function, his theory captured the probabilistic and interconnected nature of quantum systems. Schrödinger's formulation helped unify the wave and particle nature of matter, enabling scientists to describe the behavior of atoms and molecules, which are the foundation of chemistry, biology, and modern technology. You've witnessed how humanity's understanding progressed from ancient atomic theories to the mathematical sophistication of quantum mechanics. From Democritus to Schrödinger, the journey of quantum mechanics shows how human curiosity and ingenuity can unravel the deepest mysteries of the universe. If you've enjoyed this exploration, please support our channel by liking, sharing, and subscribing. Enable notifications to stay updated on future explorations of science and discovery.